Hello everyone, new video on the channel. Never really done this before. It's been scattered all around the different who's a what's its in all my videos, and you know, might as well just condense it into one place, right? Might as well. So let's do a little bit of math. So we have, at our level, encountered lots and lots and lots of mathematics. And specifically, in the realm of chemistry, we talk a lot about exponents. Talk a lot about exponentials and exponential equations and things like this. And in order to understand exponents, we need to understand where exactly they're coming from. So exponents, of course, are repeated multiplication. And we understand this in an interesting way when it comes to negative exponents as well. So x squared is going to be x multiplied by x. However, x to the negative second is what? The same as 1 over x squared, which is the same as 1 over x times x. Yes? And it is through these exponents that we understand scientific notation, which is something that I've realized anecdotally a lot of students actually struggle with. Scientific notation is a bit foreign, right? At least to a non-metric mind. I feel like if you're metric-minded, the scientific notation makes a little bit more sense. We don't really use the scientific notation outside of science. And in science, everything's really metric. So I think they kind of go hand in hand, right? What is scientific notation? It is the ability to express any number as an exponent of 10. And use these powers, or not as an exponent of 10, with an exponent of 10. And use these powers to simplify. So for example, the metric system has a scale. And there are base units and then variations on that scale. So what are our base units in scientific notation? Can someone name what I mean by a base unit? One of them is, well, that's different. Those are prefixes. A meter. We have a meter. A gram. What else? Huh? A liter. What else? We have a second. What else? Well, that's a combination of a bunch of stuff, right? We're going to get there. These, interestingly enough, when you talk about the real world, do you walk around saying, oh, well, I weigh X amount of grams? No, you say kilograms, right? So clearly, there's something else that's going over here. So this is boom, 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 the ending. And onto those base units, we add prefixes. And it is these prefixes that are determined by scientific notation. That's the bridge. Those prefixes are determined by scientific notation. Let's talk about our prefixes. Some of them have no prefixes. And that 0 stands for something. It's multiplied by 10 to the 0. No prefix means multiplied by 10 to the 0, which is the same thing as 1. Anything to the 0 power is 1. We have something known as, let's go down this way and up that way. We have something known as a deci, a little d. Deci. Little d is what? 10 to the minus 1, which is equal to 1 over 10. Correct? 1 over 10 to the 1, which is 1 over 10. we have something known as centi, which is a little c. That's 10 to the minus 2, which is 1 over 10 squared, which is 1 over 100. I'm going to erase these base units. Is that OK? We have milli. You know what? Let's do this a little bigger. Let's do our prefixes, our scientific notation prefixes. So we have the base. We have deci, D, not deci like me. It's the white way of pronouncing that. It's deci, by the way. Or deshi, if you're from Bangladesh. Deci is 10 to the minus 1, which is equal to 1 over 10. Right? This is the scientific notation right here. Yes? 10 to the minus 1. You have centi. Remember, with an exponent of 10. This is an exponent of 10. Centi, little c, is going to be 10 to the minus 2 equal to 1 over 100. 1 over 10 squared. We have milli, little m, 10 to the minus 3. 1 over 10 to the third, which equals 1 over 1,000. We then have, what's after milli? Micro, which is a mu, like that. We can do micro, mu, which is 1 over, or sorry, it's 10 to the what? 10 to the minus 6. 1 over 10 to the 6th. 1 over 1 and 6 zeros. 1 over a million. With an M, a million. What's that for micro? Nano. N, little n. 10 to the negative 9. 1 over 10 to the 9th. 1 over a billion. Now we're getting real small. You have pico and blah, 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 and whatever it is. This is kind of where we stop. How do we go up? There's only 2 you need to know. How do you go up? Technically, you could know 3. You could know deca, the big D, deca. But you really need to know m, mega, which is, what's mega? Is mega 6? Or is it 2? Someone double check. Let's do the one we do know. Kilo. Okay, 10 to the what? Kilo is 10 to the third, which equals 1,000. Mega 6. Mega, big M, 10 to the 6th, a million. These are the things that you multiply the base units by to get this. Yeah? So if I say that I have 125 milliliters of a solution, I'm saying that I have 125. The milli is in the place of a power of 10. Do you see how it's basically squished up next to that number? That means it's being what? Multiplied. Multiplied by whatever milli is. Milli is 10 to the negative third. That's how you do scientific notation. And now you fix that. 125 times 10 to the third is awkward. I'm going to move this back 2 units. I wanted to move it back 3. I already moved it back 2. That means I have to move it back 1 more time. 1.25 times 10 to the negative first liters. Do you guys see that? You guys see how that works? Yes? If I told you I have 0.00475 grams in a solution, what is this in the simplest scientific notation possible? Let's get the decimal place to where it needs to be. 1, 2, 3. 4.75. In order to get back, I need to divide by 1,000. I can multiply by 10 to the negative third grams. This 10 to the negative third, I have a name for that. What's the name? Milli. This is 4.75 milligrams. You see that? This also allows you to do some interesting math. Let's say that you had something that was 1.55 nanograms. And you wanted to split this into 5 portions. What would you do in order to do that math? I would take this, go like that, and say 155 times 10 to the negative second nanograms, temporarily. Looks weird, right? Looks weird? Now I divide this by 5. And I get what? 35 times 10 to the negative second nanograms. And now I move it back. 31. 0.31 times 10 to the negative second nanograms. Or 3.1 times 10 to the negative first nanograms. See how you can manipulate the decimals however you'd like? Just make sure how many places you move them. If you move something back, just remember you got to move it back forward in your exponent. If you move something forward, you got to move it back, right? You're multiplying, dividing by a power of 10 every time you move a decimal place. This is why we call it the base 10 system. Does that make sense? Other societies in the past used different bases. I think one of them had like base 4 or something like that. Binary is base 2, right? Like when you're coding, it's base 2. That's why you have like 64-bit, 128, 256. Any questions about that? So you guys know how to convert between the units. If I gave you something like 0.5 liters and I asked you for milliliters, what would it be? Top of your head? Huh? 500. Because you multiply by? I'm asking you to turn 0.5 liters into milliliters. Well, milliliters is 10 to the negative third times the number of liters. Right? So in order to reverse that, we're going to multiply by 10 to the third, right? So we're going to get 1, 2, 3, drop your zeros, 500 milliliters. You guys get the whole jumping, drop your zeros? That's like something you learn in like grade school. You probably forgot it long ago. You haven't done that in a while. It's just a refresher. You can also do it another way. And this is something I really like to show for people to flex their muscles and get used to this sort of way of thinking, especially when it comes to general chemistry. 0.5 liters multiplied by 1,000 milliliters per liter. This is dimensional analysis. Liters go away. 5 times 1,000 is 500 over 1 milliliters. This helps when you're doing chemistry, actual chemistry. Because eventually it's not just going to be milliliters, it's going to be like 4.27 whatever divided by the number of moles within that thing, and then you multiply by, and it gets crazy. Physics and math and chemistry always do it like this, dimensional analysis, right? For example, someone told me earlier that a joule is a base unit. Vishal told us earlier that a joule is a base unit. In physics, it is. You can talk in terms of joules. We have to get there somehow. Because what is a joule? It's a unit of energy, right? It's a unit of energy. Well, we have so many different ways of calculating energy, correct? We have kinetic energy, which is equal to 1/2 mv squared. We have gravitational potential energy, which is equal to mgh. We have spring kinetic energy, which is the spring potential energy. What's the symbol for that? Spring potential? It's just energy. 1/2 kx squared, correct? Then we have something like, what else? What's another form of energy we have in physics? Yeah, so the potential energy right here. So all of these are actually built up of base units. because the mass is in kilograms. G is in meters per second squared. Height is in meters, right? So physics has very appropriately named units. Physics uses KMS units. Very appropriately named, because physics makes me want to KMS. It really does. I hate it with a passion, which is hilarious because my favorite branch of medicine is completely based in physics, which shows you what a masochist I am, how much I must hate myself, because I love cardiology, and it's just physics. But it's physics that makes sense, you know? You win some, you lose some, right? OK. So in kilograms, meters, and seconds. So let's take MGH. M in kilograms. You're multiplying by G, which is in meters per second squared. And you're multiplying by height, which is in meters. Just multiply across the units. You get kilogram meters squared per second squared. And is that not a joule? So you can actually break this down. And this becomes super helpful in the physics section when they ask you, what are the appropriate units for this specific expression? They're going to give you a formula. They're going to say, what are the appropriate units to express this complex pattern? Go back to the equation, sub in all of the units, do the analysis, and get to the answer. For example, energy over time is known as what? Huh? Is it power? It's power, correct? Because we have joules per second. Joules per second is known as a, what's the unit of power? A watt, right? Not a what, a watt. Joules per second. We just did joules. Divide that by seconds, which means kilogram meters squared per second squared multiplied by 1 over seconds. Kilogram meters squared per second cubed. That is a watt. And you can do this that way. And honestly, if you're really bad at physics, you could take the 15 minutes before the MCAT, when they have the big tutorial and everything, like as if you haven't ever sat for a full length before, and write out every single one of your complex units in their KMS form. And it will greatly help you on the exam. I didn't do it, because I knew them, because I wrote them down so many times, but you could do it. Make sense? Very good. Enough about scientific notation. What is a logarithm? It answers a question. The logarithm answers what number let me phrase this properly. Should I place as the exponent of my base to get a desired outcome? This all makes sense in a second. Logarithms have a base. It's hidden usually. They don't usually write it right there. And you're taking the log of a number, and it's going to spit out an exponent. That is not e 2.718. That is an exponent. I'll clarify when it's e 2.718. It begs the question, I want to find this number. And I want my exponent to be the number that I raise this base to get that. So you can rewrite this another way. Log base number of exponent, log base number equals exponent, is the same thing as saying base to the power of e equals n. This is called the Ben rule. This is how you should understand logarithms. When you see a logarithm on the MCAT, rewrite it like that and see if you get any closer to your answer. Most logarithms are base what? 10, like our decimal system. So if you see something like this, log of 100, what's the answer? 2. Why? Because basically we're saying log base 10 of 100 equals, and remember, log base number equals exponent b to the e equals n. We are begging the question, 10 to what power equals 100? That's easy to see that x equals 2. This is how we understand logarithms. Everyone follow so far? Let's shake the boat a little bit. Logarithms are notoriously difficult to do by hand. Which is why when I tell you that you have an acid known as acetic acid with a pKa of 1.8 times 10 to the negative fifth, and I want you, a Ka, 1.8 times 10 to the negative fifth, and I want you to calculate me a pKa by hand, you might be lost. That's okay. What is this little letter P in chemistry? P means take a negative log. Oh God. Not only a log, but negate it. Well, negate the whole thing is what we mean. So P of x is to take the negative log of x. So take the log of x and negate it. So the pKa of this is going to be the negative log of 1.8 times 10 to the negative fifth. Yes? Say yes. Someone commented the other day. They said, why should we say yes? And I said, because I said so. Because I said so. You don't have to. It just makes it fun. Makes me feel like I'm doing something. How would you approach that? It's easy to say, it's not that far off from 10 to the negative fifth. It's not that far off. So why don't I just do this? Negative log, 10 to the negative fifth. 10 to what power is 10 to what power is 10 to the negative fifth? Negative 5. Negative 5, oh my God, it's 5. Easy enough. If you desire mediocrity, that's fine. If you want to be special, let's teach you how to be special. So the question is negative log of 1.8 times 10 to the negative fifth. Log rules. This is where the pen starts scrambling. Sorry, other way around, right? No, right? Hold on. Oh my God, I'm rusty. Let's do the ones I do know. Oh yeah. I was right the first time. Never doubt yourself. People, what else am I missing? I think that's kind of it, right? Yeah, but they're not like, These are like kind of arithmetic, like intuitive, you know what I mean? This is really important for us. Those are your log rules. And I'm going to add some approximations. The log of 2 is approximately what? 0.3. the log of 6 is approximately, anyone watch my old videos? Anyone remember? Log of 6 is 0.8. And the log of 8 is approximately 0.9. 2, 6, and 8. Now let's do that. Negative, let's actually just break this down. We have a multiplier in there. Let's break that. Log of 1.8 plus log of 10 to the negative fifth. This is asking 10 to what power is 10 to the negative fifth? That is negative 5. Log of 1.8 is a little bit less than log of 2. Tiny bit less. How much less do we want to go than 0.3? 0.25, let's say. .25 plus a negative 5 is what? Negative 4.75. Positive 4.75. I love this part of the lecture. Someone go online and tell me what is the pKa of acetic acid. What was it? Actual 4.76. It's a hell of a lot better than 5. We were within 1/100th of the answer. This is how you estimate logarithms. Who taught me this? Shout out to Professor who? Midlitsky. The GOAT. You think I'm harsh? I asked him a question once about chirality. He looked me dead in the eyes in front of a room of 50 people, and he said, "There's no way you're stupid enough to ask me that question in public." I went on to become one of his favorite students. I succeed and thrive off of teachers who are very harsh. I thrive off of it. But there's a line. There's harsh and respectful, and there's harsh and disrespectful. It's very hard to toe that line. Hope I'm on the right side of the line. Here's hoping. Anyone have any questions about this? Do you guys get this? This makes sense?
Do we just have to memorize like the 2, 6?
Yeah, that's just pure memorization. One more trick that some people don't know is that like 47% of 50 is what? 50% of 47. Swap it, because it's just divided by 100. Just swap the 100. So instead of doing 47% of 50, do 50% of 47, which is 23.5. That'll help on the MCAT as well. Yes?
I think there's this thing where like, if you do like something like 3.2 times 10 to the negative fifth, anything like 3.2 approximates to like 0.5, like the decimal.
Yeah.
So like helps you like.
Totally, yeah. So Vishal just brought up a good point that like 3.2 is the 0.5 range when you do a log, right? Which you'll see that it jumps from like 0.3 to 0.8 over here. So in between here, because it starts like that and then it goes up, in between here you'll have 0.32, and that is going to equal your log of 0.32, or sorry, log of 3.2 equals 0.5, right? So you can use that as a middleman if you'd like. Let's do one more thing. I want to very quickly show you some of the most important derivations in chemistry. We're not going to do calculus, don't worry. There's no calculus involved here, not that type of derivation. You have a formula, delta G equals delta H minus T delta S. You remember this? You also have delta G equals negative NFE. And you have delta G equals, what's the last one? Huh? No. You do have RT in there. RTLNK. Except she's wrong. Negative RTLNK. What is that ln over there? It is a log, a natural log. It is log base e, which messes up our Ben rule a little bit, but this is not e exponent, this is e 2.718. E is Euler's number, approximately equal to 2.718. So it is log base 2.718 of a number is equal to the exponent. This is exponent e. So when you take ln k, you're doing log base e of k equals whatever you're looking for. And e is equal to 2.718. Different e. I'm sorry, but we don't have more than one term for that. So how do we reverse this? So let's say x. So if it was b to the e equals n, now it's going to be e to the x equals k. Keep this in mind. And that's e 2.718 once again. So you reverse a natural log. These three are associated with one another. Negative RT ln k equals negative NFE equals delta H minus T delta S. And you can swap them around and jump them around and everything. What is K? It answers a question. To what ratio are the products favored over the reactants? If K is less than 1, the reactants are favored and the forward reaction is not favored. If K is greater than 1, and the products are favored and the forward reaction is favored. Make sense? If you were to take a log of a number less than 1, or in this case less than 2.718, you will get a negative number. That negative number will multiply by this negative, giving you a positive, making this non-spontaneous because the forward reaction is not favored. You don't have enough product. Does that make sense? Same thing here. We did the E earlier. If the E of the oxidized and the E of the reduced, if you subtract them out, you get positive because the thing that wants to be oxidized is getting reduced. This becomes negative, positive, positive, non-favorable. Make sense? Yes, because you usually want the larger thing to subtract by the smaller thing, red minus ox. But if you get the smaller thing, subtract out the bigger thing, then you get the opposite, negative, positive, non-spontaneous. Now, I just told you two ways that we can get to non-spontaneous things. So if I set these equal to one another, and I get rid of these negatives, divide by the negative on both sides, and I divide by RT, and I reverse the natural log, I get a famous derivation that equates the degree of favorability of redox reactions to the amount of product and reactant formed within that redox reaction, multiplied by constants. The only thing that changes here is the E. This is a constant, that's a constant, that's a constant, that's a constant, that's the number of electrons in the reaction. Very famous derivation. You will be asked to do that on the MCAT. I've gotten asked this like 4 times. You can do the same thing with divided by a negative 1, NFE equals negative delta H plus T delta S. I hate writing it that way, so I'm going to say NFE equals T delta S minus delta H, divide by NF. And you get a new way of calculating the electrical cell potential using the change in entropy and enthalpy of the reaction divided by the number of moles of electrons and Faraday's constant. It's just unit manipulation. That's it. So if you were to have all of these inside, you don't even need all of them. All of these are constant within the reaction. You just need an E, you can figure out a K. You just need delta H and delta S, you can figure out the E. You can just toss these around one another depending on what you have. Use what you have to your potential. Analyze everything and see what you can use. Right? This is what MCAT mathematics is really about. What time is it? 6:30. Any questions about that? Speak now or forever hold your peace.
For the R part, is that the one where like the value can change from like 0.08 something like that?
They would probably, for R, they would probably give you the value whenever you need to use it. I don't think I've ever had a question where they didn't give me the value. Any other questions? No? You're going to do something really controversial because we have time. Chapter 6, chemical equilibrium. Let's flash back to general chemistry. Now that we know all of this. How are we looking? Good? Equilibrium, what is it? Huh? No net change. What does that mean? Sounds like a soundbite to me if I've ever heard one. Exactly. This is known as dynamic equilibrium. There's things happening on both sides, but nothing changes. We have a reaction, A, and previously we've seen reactions like this. A and B makes C and done. Khalas. Shesh. We're finished. Right? Shesh means done in Bengali. Say amen. Now we're saying that it is possible that you have A and it makes B, or basically, you do A and B, and it makes C, but C also decomposes back into A and B. And there's a rate of the forward reaction and a rate of the reverse reaction. We're going to say rate, and we're going to say rate. And at equilibrium, and we can say dynamic equilibrium, this means that rate 1 equals rate 2. So that over time, the concentrations of A, B, and C remain steady. For example, an A-B dynamic equilibrium would sort of look like this. A, B. A goes up, B goes down, but they level out and they stay there. It's time. This is concentration. So what do we need to know in order for equilibrium to work? We need to know something known as the molarity. Because this is happening inside of a solution. Usually when you get an equilibrium, it's done inside of a solution. Molarity equals moles over liters. And that molarity is what we write inside of the concentration, these brackets. Equilibrium is judged by something known as the law of mass action, also known as K. You have AA plus BB in equilibrium with CC plus DD. Your law of mass action states that C to the C power times D to the D power over A to the A power and B to the B power is equal to an equilibrium constant K. This is saying that the ratios of the concentrations of the products and the reactants at equilibrium at a specific temperature are the same over time. And it's going to be equal to this, because those concentrations hold steady at equilibrium. And this allows us to gauge which side of the equilibrium is actually favorable. Because what do we mean by favorability? What does favorability mean in chemistry? It means what? Huh? Stability. Favorability means stability. So whichever side is more stable, we're going to form more of it. Does that make sense? So if the products are more stable, we're going to form more product. This ratio is going to be greater than 1. Numerator greater than denominator, you get greater than 1. If the reactants are more stable, the reverse reaction is more favorable. That means the K is going to be less than 1. Does this mean that the rate of the reverse reaction is greater? No. The rate of the reverse reaction would be the same if K is less than 1, but the amount of reactant that we have is greater. Meaning that there is more product turning into the reactant at that rate than reactant turning into product at that rate. Does that make sense? This is best understood when we talk about acids and bases. For example, within the mathematics portion of this lecture, we talked about acetic acid and how its dissociation inside of water will lead to an equilibrium with hydronium and acetate. If you are classical, you can write it like this. For any given acid with the formula HA that dissolves inside of water, it gives off hydronium and A minus. And by writing the K expression of this, where all the coefficients are 1, we get something known as K equals H3O plus times A minus over HA and H2O. Yes? No. There's no H2O in the equilibrium equation. Can you tell me why? Huh? What concentration? Is there a concentration of water? Huh? What do you mean it's built in? Huh? It's not a spectator. Why is water not in the equation? Huh? Yeah. So that means what? Huh? Not necessarily. If I erase the water. Concentration in what? In water. It's already there. It's the brackets. Concentration of HA in water. HA minus in water. H2O plus in water. It's already there. It's taken care of. Now, K is a lie. K isn't a real thing. The law of mass action isn't a real thing. You get to physical chemistry, you learn that it's actually the activity of each of these molecules, and water has an activity of 0. So who said the activity? Someone said it. Like, it doesn't change over time, something like that. I don't know. Yeah, activity. You're pointing to the fact that it has 0 activity in solution. So it is a spectator in that sense, but spectator means something different in general chemistry than in physical chemistry. Have you taken physical chemistry?
I'm taking the next one.
Okay. This is known as K what? K A. The equilibrium constant of acid dissociation. Who's traumatized? I am. Spent a lot of my life with Ka. Very abusive relationship. So, someone write me the Ka expression for acetic acid. C2H3O2, let's do this. Divided by? Very good. Yes? Correct? It's the Ka. I'm telling you that the Ka of this is 1.8 times 10 to the negative fifth. No units in Ka. That means that what's greater, the products or the reactants? That makes this a very strong or weak acid? Weak. There's so much left over versus the amount of acid we actually get. This is a very weak acid. Strong acids have Ka's greater than 1. You're going to have very little reactant for the amount of acid that's produced. Does that make sense? Yeah?
I have a question. Normally we talk about carboxylic acids being like strong, so how come
They're not strong. They're relatively strong.
Oh.
We talk about carboxylic acids being relatively strong. The word strong in chemistry refers to a list of acids that you must know by heart. Anyone know them? Start from the top, not HF, but the one after. HCl, then go down the list. HCl, HCl3, HCl4, good. HBr, HI, HNO3, H2SO4, done. 7, that's it. We already did the pKa discussion. That's part of this lecture too. Already did the pKa, we talked about that. We calculated that whole thing. We saw that it was negative. Or sorry, we saw that it was positive. So you see how weak acids have positive pKa's and strong acids have negative pKa's because you're taking the negative log of a larger number is going to give you a more negative number. And negative log of a smaller number will give you a larger number. You're negating whatever it is, correct? And the whole train of thought there is that the negative log of Ka is basically asking you to flip the narrative, right? It's saying, well, if the products are high and the reactants are low and we take the negative of that, then we're taking the log of a very large number, which is going to be a large number. And if we negate that, that's going to be a negative large number. So strong acids have very low pKa's, negative pKa's. Whereas if this were a small number like this is very small, and this is very large. That's a very small number. Take the log of a small number, you get a negative number. You negate that negative number, you get a positive number. You guys follow the math there? You guys follow the train? Yes? You guys look shot. I'm not going to lie. Everyone in this room looks like they want to crash right now. Especially you. We took a 4-hour exam this morning. Well, 2.5. talk about one more thing that influences equilibrium. We good on this? This also happens with like metal solubilities and things like that, but it hardly ever shows up on the MCAT, and if it does, it's the same thing as this, but without a denominator. That's it. You guys know how to do ice charts? We'll do it. I don't want to do it right now. Someone make a note of it. You know, someone write it down somewhere. Someone like set a reminder for 2 weeks from this very moment, and I'll teach you guys how to do ice charts. What time is it? At 6:46, 2 weeks from now, set a reminder, and I'll teach you how to do ice charts. It's going to come up. I'm going to be in the middle of it. I'm going to be like, damn it. Drop everything I'm doing, teach you how to do an ice chart. It's going to take 5 minutes, but I just don't want to do it right now. This is more for my orgo people, but it comes up in equilibrium a little bit just because we're able to explain this. Thermodynamic, kinetic. What is the difference between something known as a kinetic product and a thermodynamic product? The thermodynamic product is more stable. Pretend that says thermodynamic. More stable. More energy initially to overcome high activation energy. So the thermodynamic product here will actually be due to the Zaitsev elimination of a hydrogen from the more substituted position in the ring. A Zaitsev style elimination. Zaitsev, Hoffman, you guys remember that? Yeah. That's the correct nomenclature, right? It's been years since I've done orgo. Hoffman's the other thing when you oxidize it, right? And then it has to line up the proper way. Is it? I don't know. I'll read up on it again before you do orgo. That's the thing. Like, it takes me like 10 minutes to just look over. I'm like, oh, I remember that. I've learned it so many times. And that would mean that the kinetic product is the one that is more unstable. This is the one that's made by low energy initially. You don't put in enough energy to overcome a high transition state. You make a little sloppy of an error. This is the one that's made by your ridiculously agitated bases that don't want to wait for anything. LDA, LiALH4, potassium terbutoxide, don't want to wait for anything. This is more of an organic chemistry discussion, but I just wanted to bring it in because the kinetic will actually do what? It'll come back. Because what's happening here is that you have your initial state, you have a little bit of energy, and then you have this kinetic product. Then you have that initial state, you have a lot of energy, and then you have that thermodynamic product, much lower in energy. So this is your kinetic, and this is your thermodynamic. This is your EAK, activation energy of the kinetic product, and your EAT, oh, I want to eat, your thermodynamic activation energy. Now the thing is, when you come here, you can imagine that you can just climb this hill and come sort of back, right? That's not a huge hill to climb. It's hard. But you can climb that hill. Can you climb this hill? No, you're not going back. So kinetic products can actually participate in equilibrium, and you can fall down the hill and roll back up and fall down the hill and roll back up. But once you get enough energy to climb this hill, you don't roll back up. You're stuck as a thermodynamic product, as that is very stable. And remember I said that the forward reaction getting stuck or coming back or whatever it is based on the stability of the product you're making. Very stable, it's not coming back. Less stable, it might come back. Does that make sense? This is the same thing as a strong acid dissociating. When a strong acid dissociates, it creates an incredibly stable base. And that stabilized base is not going to come back and be something that it doesn't want to be. It's not going to be this unattractive, unstable, very reactive, very angry acid. It's going to stick around as the stable thing that it became because of these 5 factors that stabilize conjugate bases. A little look into your future. We will have an entire discussion about that along with our resonance lecture. Yes?
I have a question. So even though the activation energy is higher for making a thermodynamic product, it's more stable because the reverse reaction is literally impossible?
So you're saying that the activation energy of making the thermodynamic product is higher.
Yeah.
Why is that?
I don't.
Because we're making a more stable product.
Oh.
Yes?
Is the KQ for the reverse equal the inverse, basically?
Ooh, I totally forgot to talk about Q. You just reminded me.
1 over?
So KEQ, you said? The KEQ of the reverse reaction?
Yeah.
Yeah, so you just flip it. Because the products become the reactions become the products. You totally reminded me that I forgot to mention Q. We have K, correct? And K is each of those things at equilibrium. Each of those products and reactant concentrations at equilibrium. This is a really dumb concept to get confused about because it's just that people don't just explain it properly. It's not your fault. People just don't do this right. So how about Ka of acetic acid? Or let's just do any acid. Sorry. This is K. At equilibrium. At dynamic equilibrium, the rates are equal. At that specific temperature, it is a specific number, right? If you are not at equilibrium, we say that you have something called Q. Q is the same thing. But it's all at a specific time. We say that this is only equilibrium, so we don't need time. Just is it at equilibrium? If it is, it's this. If it's not, we have a specific time. Q can be greater than K. That means there's too many products, right? And if Q is greater than K, reverse reaction preferred. Because you want to make more reactant to get back to K. The desire is to always be at K. That's equilibrium. The desire is to be at equilibrium. So that means that if Q is less than K, what reaction is preferred? The forward reaction. And if Q is equal to K, then why are you doing this? You're at equilibrium already. That's it. Make sense? One more thing. Let's do one final recap on Le Chatelier's principle. And we'll do one practice problem. Oh my God. We never do problems. Chatelier's principle states that any stress in a system at equilibrium will make the system respond in a way that alleviates the stress. We talked about it in the bicarbonate buffer system. Let's talk about it in terms of acids and things of the sort. I'm going to tell you that this flask I'm about to draw is at equilibrium. Question. What happens to the concentration of acetic acid after the addition of 50 milliliters of 0.745 molar NaC2H3O2? You do not need any math to answer this problem. Who knows the answer already? You should know it the second I write it. You know the answer?
Well, if you increase that stuff, then you have to increase it.
Exactly. That's it. What is NaC2H3O2? It's Na plus and C2H3O2 minus. This is that. That is a stress that disturbs the equilibrium. What is Q now? Q is what then K? Greater than K, because the products just went up. And if Q is greater than K, then the reverse reaction is favorable. We go back, which increases the concentration of this by transitive, and we get an increase in that concentration. Done. We drop the amount of acid because it's combined with the base to make that. Yeah, what's your question?
This might be like not in this chapter, but do we also need to tie in like common ion effect? Like,
That is the common ion effect. What is the common ion? Acetate.
does that make it like harder to
Because there's two reactions. It's called the common ion. I think a lot of people don't understand why it's called the common ion effect. This is why it's called the common ion effect. Common ion. Common ion. The dissolution of this salt and the dissolution of that acid share a common ion. So the addition of that salt disturbs the equilibrium of the opposite reaction, increases the products, increasing the Q, disturbing the equilibrium, favoring the reverse process, increasing the amount of acid. But they won't ask you what happens to the concentration of the acid. They won't ask you what is the concentration of the acid after the addition. They will ask you what happens to the... Who's taking the MCAT before? What do they ask? What happens to the what? It's a very specific phrase. Do you know? Anyone know? What happens to the percent dissociation? What happens to the percent dissociation of that acid? Let's say that acetic acid has a 1.8% dissociation. Very weak, right? Very little of it gets dissolved. The percent dissociation will go even further down because the percent dissociation is based on the K, the Ka. Make sense? Equilibrium is not hard. Promise you it's not hard. Until it is. Everyone got that? You guys hungry? Let's go home. Thank you guys so much for watching. I'll see you next time.